Once the local mass and local stiffness matrix for each element is calculated, we're going to assemble those local matrices into our global matrices, our global mass and global stiffness matrix. Again, like we did for our axial problems. But we want to keep in mind now how our degrees of freedom work. Our degrees of freedom are going to be, the odd values are going to be our vertical displacements, and the even degrees of freedom are going to be our angular displacements. And in general, since we're going to be ignoring damping once again, we're going to have this mw double dot plus kw equals f. Now, we're going to concentrate on autonomous systems, so for this course, our right-hand side is just going to be the zero vector. We're not going to have forcing applied to our system. But we still need to assemble the matrices the same way, superimposing all of the local matrices onto their corresponding degrees of freedom. And here it's going to be even more useful to use that mapping of knowing what degrees of freedom are attached to which element and the order that they're going to be attached. So we know what rows and columns to superimpose the local matrices into the global system. With the global matrices built, now we can go and enforce our boundary conditions. So the fixed degrees of freedom are going to be incorporated by modifying that global mass and global stiffness matrices. And we do it in basically the same way we did for the axial problems. Since we're only going to be dealing with homogeneous boundary conditions in this course, what we're going to be able to do is remove the ith row and the ith column from the mass and the stiffness matrix to enforce these homogeneous or zero boundary conditions. In the axial problems, we only were doing this when we had zero displacement boundary conditions and didn't worry about when we had zero strain. Similarly, for these transverse problems, we're only going to eliminate the rows and the columns for the degrees of freedom that have zero vertical displacement or the rows and columns for zero slope. If we have zero internal bending moment or zero internal shear force, no modification to the stiffness or the mass matrices are needed. And again, what we want to keep in mind that is sometimes hard to remember here because we have twice as many degrees of freedom as we had in the axial problems. Odd indices and therefore odd rows and columns are pertaining to displacements, vertical displacements, and the even indices pertain to the slopes of the nodes. And if you have non-homogeneous boundary conditions, you're going to need to use a different technique outside the scope of this course. So once we eliminate the proper rows and columns as needed to enforce these homogeneous boundary conditions on displacement and slope, then we are ready to find things we're interested in our solution. So we can use this M and this K matrix to first find the natural frequencies of the transverse system. Again, keeping in mind that the number of natural frequencies we're going to be able to find is going to depend on how many elements, how many nodes we meshed our system to have. And like with axial problems, the more we have, the more the estimates are going to improve as we go from lowest natural frequency to higher natural frequencies. So we still need to be concerned with convergence of our solutions here. But once we have our natural frequencies, once we have our mode shapes, then we can proceed in a similar manner to how we did it for axial problems. We can then, once we show convergence, then go and use principal coordinate analysis with our initial conditions to solve for the displacements and the slopes of all of our nodes. So actually, we're going to go a little bit further with what we can do with FEA with the transverse beams than we did analytically. Analytically, we stopped with just looking at the natural frequencies, and it gets much more complicated in order to find the behavior of the system. However, with finite element analysis and principal coordinate analysis, turning it into a multi-degree of freedom system, we're going to be able to actually solve for these displacements over time based on initial conditions and free vibrations.